Okay. Okay, so I have this talk. I don't know if this is a talk or a presentation. I honestly don't know. It can be both, it can be either. So fix one bottleneck, create another. So the goal of this talk is not to teach any specific concurrency primitive, though if we would want that, we'd have to have another talk about that. But it's just to show how performance bottlenecks evolve and how each optimization introduced a new class of problems for me. Like I was optimizing, and when I optimized, I got new problems to solve via the optimization. Yeah, so that's just the purpose of this talk, just to show you a project I worked on and how each optimization introduced new problems for me. Yeah. How the project started. Last December, I wanted to do the Advent, and for my Advent, I wanted to learn new C++ features, and I got to read about modules, and I really wanted to use modules. I just I wanted to use modules. So what's the best way to use modules than creating a new project, right? So I thought I can create probably a new toy project, and I would get to see how modules work and how they integrate well with build systems, specifically CMake. So I built a directory scanner, and I thought it would be a simple project, just something that just scans a directory, right? And it wasn't. So the name of the project was Phanis. Phanis is a Greek, a primordial Greek god. Anyways, so how the project works is just a simple CLI tool, kind of like your file explorer in Windows, but for CLI. You just give it a directory that it takes as a root. It works through the directory, scans the directory for subdirectories and files, and then builds an in-memory tree of the file system and then analyzes it. Like things like you can get some analysis like, oh, these are the 10 most recent modified files. These are the empty directories in these directories. These are how many subdirectories in this directory. These are how many files in this directory. This is the largest file in this directory. This is the smallest file, and all of that stuff. Yeah. So that was just the project, a simple CLI file explorer, something of that sort. Yeah. So I figured that out. There was a bottleneck in the scanning, right? Scanning the file system was too slow. And if the scanning is slow, every other stuff is slow. The build tree has to wait for the scanning to finish before it can build the tree, and then before we can run the analysis. So scanning through the file, the directory, scanning through all the files and the subdirectory there were just too slow, right? And I was using a simple iterative DFS, just single threaded DFS, where you just run through the directory and the subdirectories and build the tree. And it was working fine. Everything was working perfectly fine. It was building the in-memory tree. It was also doing the analysis perfectly. The only thing was that it was just too slow, right? And then, yeah, for the simple DFS on Linux, where I had about 2 million files and about 500,000 directories, it took about 15 seconds to do the scan, right? And then for Windows, where I had less files, I had about 1.2 million and 200,000 directories. It took about a minute and 5 seconds. So that was just too much. And I wanted to look for a way to reduce these timings. I mean, a minute and 5 seconds just to do a scan to know if to analyze some directory was just too much. So I figured I had to reduce these timings. What can I do to make this time slower, to make it faster? So I looked around and saw that the directories were not dependent on each other, right? So we can make this multi-threaded. We can have one thread scanning a directory and another thread scanning another directory, and then they are building the in-memory tree at the same time. And since the directories are not dependent on each other, it can be easy to use multi-threading to do this, right? So you can have one directory, one thread scanning one directory, another thread scanning another directory, and there won't be any issues since these directories are not dependent. And yeah, so I figured I could use a thread pool, a simple thread pool that we could use to make this easier. So we have this global tax queue, and the main thread of the program, when you impute your the directory you want to scan, it takes that as the root, right? And then imputes this root into the global tax queue, right? And when it does that, it alerts the workers. It wakes up the thread and says, "Oh, there's work here to be done." So the first thread takes the root directory from the global tax queue, scans it, and anytime it comes across any subdirectory, it pushes the subdirectory back into the global tax queue for another thread to go there, take the subdirectory, scan it. If it sees a subdirectory in the subdirectory, it adds that back into the global tax queue. So in this sense, the threads are both producers and consumers of tax because they can take directories from the global tax queue, scan it, and when they find subdirectories in that directory they took, they will push it back into the global tax queue for another worker or another thread to pick up and scan. And when they are done scanning their own, they go back and check if there's still some work to be done in the global tax queue, and they pick it up and work on it. I mean, and that was efficient, right? That was efficient. I had some group of threads and
has their own queue. So when they wake up, the first thing that they do is to check their local queue. Do I have any tax on my local queue? If they don't have a tax there, they check the global queue and check, oh, is there a tax on the global queue I can pick up? If there's no tax in the global queue, they go to bed, right? And if there's a tax in the global queue, they pick it up, and then subsequently, if they find subfolders in the folder they are scanning, they push it into their own queue. So in an ideal situation, if everybody has work to do, there will be no log contention. The only time there'll be log contention is when they want to go to the global queue to pick up. And once they've done that pickup, the subsequent scans and subfolders that they find, they push it into their own queue. So nobody is fighting over the log with anybody in that scenario, right? The only issue was this cost load imbalance, because let's assume that worker one picks up a very deep folder that has lots of subfolders, and when it finds those subfolders, it will push it into its own queue. And then let's say worker two picked up one folder that just has 2 files in it, and then he scans it and he's like, okay, I'm done. There's nothing else to do. Worker three the same, worker four the same, and then worker one has this chunk of work to do, and only worker one is suffering, and the rest of the threads are just sleeping because they have nothing to do. This is just like you're going back to single thread DFS work, right? And I felt this wouldn't work, right? We have these threads that are looking for work to do. There's nothing for them to do. But we have this other thread that has lots of work to do. Is there a way to like balance this? Right. So is there a way to balance this situation? And yeah, there was a way to balance it. How about threads that don't have anything to do? When they check their own local queue and see, oh, there's no work on my local queue, and then they check the global queue and see, oh, there's no work on the global queue. They can check for their neighboring threads and say, is there anybody here that has too much work to do? Maybe I can steal some work off you, right? So let's imagine worker two wakes up and say, oh, worker one has too much work, and then it steals off half of this work from worker one, right? Kind of lessen the load for worker one and puts it in his own queue and starts working on it. And then worker three wakes up and say, oh, worker one still has work to do. He goes to worker one and steals some of the work, right? And starts working on it. And everybody helps to lessen worker one's load, which would make the thing faster on the long run, right? Because worker one is not the only one working on these things. Yeah, so I decided to change from using a queue to using a queue, because now we'll have two threads accessing the same data structure, right? So let's assume that this is a queue for worker one, right? So worker one would work from the back end of the queue, pushing in tags, and like it's a consumer and a producer at the same time. So it will be pushing back subfolders that it finds, and then it will also be popping out sub folders to scan and do all of that. Then again, the thieves, there can be more than one thieves trying to steal from worker one. It's not just one thief. There can be about five other threads trying to steal tax from worker one. We don't know how many there are. There can be one, two, three, any amount. So these thieves will come from the front. So that's why I changed from using a queue to a queue. because with the queue data structure, you can pop from the front and from the back, right? So the thieves will only access from the front and do their stealing from the front, while the owner only works from the back. So at least there will be no struggle. The owner will just be doing his own thing from the back, and the thief will just be doing his own stuff from the front, right? Yeah, I mean, there was still low contention because back to this place, when a thief wants to steal, right? This is a DQ, and there is still a mutex here, and this mutex is owned by this thread, right? And he's doing his work, and somebody wants to steal. If you want to steal, you have to acquire the mutex from the first worker from T1, right? When you acquire the mutex from T1, then you steal and take as much as tax that you want to take from here, and then release the mutex back to T1. So at that point, you're taking the mutex. That means T1 has to wait, right? It has to wait for you until you're done stealing before it can continue its tax. If it's pushing or popping, it has to definitely wait for you to release its mutex, right? So there is still lock contention, right? Not that the lock contention has gone totally. There's still lock contention. But the good thing here is that on an ideal situation where every thread has work to do, right? Nobody is contending for locks with anybody or mutexes with anybody. Everybody has work to do. But the lock contention only comes up when there's a load imbalance and one thread wants to steal from another thread. So that would bring in lock contention, which I felt was better than the previous one where everybody was working from one particular global queue, right? And had to always, if they want to do anything, they have to contend for the mutex. So I felt this was better, right? And I designed it and it was working. And I tried to benchmark to compare with the previous to see how far, if it's better, if it's worse, right? So for Linux, with the same amount of files like last time, it worked well. From 10 seconds, we got down to 8 seconds, right? But on Windows, we regressed from 7 seconds on a traditional thread pool with no optimization. We went up to 12 seconds. And I don't know why. I probably on the Windows, the stealing was just, the lock contention on the stealing was probably worse. I honestly don't know why Windows regressed. So I couldn't go with this number, so I was still stuck because should I go back to using a traditional thread pool where at least things were better, but Linux was 10 seconds, or should I look for a way to make this better? So I had to look for a way to remove the lock contentions from the stealing part. Yeah, so that was just the goal. Is there a way to remove the lock contentions at all from the stealing part? At least if we remove the lock contentions from the stealing part, we can see, okay, there's no lock contention again. So everything should be fine, I guess. So the goal now was to remove the lock contention from the stealing parts, right? So to do that, I had to change the DQ to being lock free, right? That was the only way I could remove the lock contention when there's stealing. If every thread's DQ is lock free, during the stealing, there won't have to be any give me your mutex. I want to have your mutex because I want to take something. I want to lock your mutex because I want to take something. No, everybody would just be able to access the data structure anytime at the same time simultaneously, right? And to do that, I had to stop using STD DQ. I had to design my own DQ because STD DQ obviously is not lock free, and if you want to do lock free, you have to design your own data structure. So I had to design my own DQ from the scratch, not something rigorous anyways. So to design that, I had to also think of, this is a data structure and it has to grow, right? You don't know how many tags these threads will be pushing into the DQ, so it can't be static. It has to be dynamic. It has to be able to grow. So, but then I don't also want to waste space. So I decided to make it secular. I didn't decide anyways, but that's just the rule of thumb, to make it secular, because in think of like a normal vector, right? A normal vector, you just have one or two operations, pushing from the back and popping from the back. And even if you take something from the middle of a vector, you still have to push the elements, right? And then you have your push back and your pop back and all of that. So it's easy to know when the vector is actually filled up. It's easy for you to know because you know when you're trying to push and the size is less than, is equal to the number of elements there, right? You know that, okay, this vector is filled up, so I need to allocate more memory for this vector. But in this DQ, it's different because remember, we have thieves stealing from the front, right? And we have the owner working from the back. So the owner might want to push and see that, oh, at the back here, there's no longer space for me to push, right? And then it allocates more space. But that's a lie because remember, we have these guys in front here taking stuff. And what if they've taken about 5 elements and there are five free spaces for this for the owner to push something? But the owner doesn't know that because he didn't get to check the front to check if this is genuinely empty, and then he goes ahead to allocate more memory, right? So making it circular would mean if the owner actually allocates memory, it means genuinely this the queue is actually filled up, right? So that helps to conserve space a lot. So that was just it. I made it circular and then I made it lock free, right? But making things lock free comes with its own issues, right? It comes with its own issues in the sense of, right, it creates problems like you have force sharing. You have to think about force sharing now. You have to think about memory ordering, and you have to think about, oh, what if this is the last element in this data structure? Who will be the one to take it, right? Like I said, it's just like a bathroom. With mutexes, there's a key. So once you enter the bathroom, you lock it, and once somebody comes to check, knows, oh, okay, somebody is here. Let me wait until when the person is out. But we lock free. There's no key. The door is just open and anybody can come in and see you, right? So moving these mutexes created problems that I had to think about. So I'll probably like go through one of them one by one. The first is force sharing, right? So with force sharing, I think you have to think of it this way. Like I said, when you're single threaded or you're using mutexes, when you're not taking things at the same time, you don't have to care about force sharing. You don't have to care about that at all. But when you have a data structure where two threads are trying to access the data structure at the same time, simultaneously, at the same time, you have to think about force sharing. So let me probably write because I will need to write. So to understand force sharing, think of it this way. The CPU or the threads are in the CPU too. The kind of they don't make changes to memory in form of bytes. They make changes in form of cache lines, right? And these cache lines can be about normally 64 bytes, right? And in this cache line, there can be so many variables or other things in memory. And it does this for optimization purposes because it believes, oh, okay, I think writing would be nice here. So let's say in your single threaded program, you can have X and Y, and then you have probably X equal to 6 and Y equal to 7, right? And then in your CPU, you have, let's say this is 3 threads, right? And then each of them have their own internal L1, L2 cache. And let's say this is shared memory between them, right? So let's say something like this. And since this in your program, your single threaded program, this is not a problem, right? Let's say 6 and X and Y are in the same cache line. Let's assume each row is a cache line, right? A 64-byte cache line. And then X and Y is here, right? And this is CPU 1, 2, and 3, right? If 3 wants to make change to Y, it doesn't just make change to only Y. It picks this entire cache line, right? It copies this entire cache line into its own, let's say L1 or L2, right? And copies it here. So you have X and Y. But this is not a problem when it comes to like single threaded or when there are mutexes because again, two threads are not making use of this, two threads are not making changes at the same time, right? With mutexes, when this thread is done, right, it releases the mutex and releases, and then the next thread acquires. It's easy, right? Because no two threads are doing the same thing, are making changes at the same time to the same data structure, right? But then it becomes a problem in lock free because we have two threads having access to the data structure at the same time. So let's say thread 2 and thread 3 in a lock-free program have access to this cache line, right? And let's assume that X and Y are for this lock-free DQ. Let's assume X is the front and Y is the back, right? And then 3 here is the owner, right? And 4 is probably a thief that wants to steal something. For the owner to push back, right, it wants to increment Y to 8 to show that, oh, I have pushed back a folder into my own DQ. And the thief wants to steal something and he wants to decrement 6. Okay, sorry, he wants to increment 6 to 7 to show that, oh, I have stolen from this index. So there's nothing in this index again, move to the next index. And the owner too is pushing back, doing his own thing. He wants to say, oh, I have added a variable, I've added a folder to this queue and I'm moving the index from 7 to 8, right? Both of them are doing honest work at this point. But the problem is X and Y are in the same cache line. So the owner copies this cache line into his own L1 cache. The thief copies the same cache line again into his own cache, right? And remember, the owner just wants to make change to Y, and there's X and Y here. And the thief just wants to make changes to X, right? They are making changes to different variables at this point, but the problem is that the variables are in the same cache line. So when the owner asks the CPU has like a way to talk to each other, the cache coherence, asks for exclusive access to this cache line and updates Y to 8, right? It updates Y to 8, right? Which it should do. But the thief at that time too wants to update X. So he tells the owner, hey, please, I need exclusive access to this cache line. Please give me this cache line. I want to update X. And the owner says, oh my God, and I already made changes to Y. That means I have to invalidate my change. So it invalidates his change and gives exclusive access to S, which is the thief, right? And the thief makes changes to X. And while he's making change to X, the owner said, wait, me, I want to make change to Y. Give me exclusive access. And then the thief gives exclusive access to the owner again and invalidates its own cache line. So they'll just be going back and forth. And that doesn't make any sense, right? The best way to do this is just to make sure X and Y are not in the same cache line. If there's a way to say, okay, X, you're here, right? How about we put Y here? So they are in different cache line. If the thief takes this cache line and copies it into his own L1 cache, it can make as much changes as it wants, right? And nobody cares. And then the owner takes this cache line and copies it into his L1 cache and can make as much changes. So there will be no back and forth movement anymore, right? I mean, that's one thing you have to look out for if you're going to do anything lock-free. You have to always account for force sharing and make sure that data structures that are used by 2 threads, right, they don't share the same cache line. Luckily enough, C++ has a way to do that, right? You can just use aligners. When you use aligners makes sure that there is a 64-byte space between each variables, right? So when you're declaring your variable, you can just use aligners 64, and the CPU knows that, okay, these 2 variables, you want them to be in different cache lines. So there will be no force sharing between the 2 of them, right? So, I mean, this is not a bad problem and the solution is straightforward. The other issue is memory ordering, right? With memory ordering, with single threading or mutexes, you don't have to think about memory ordering, right? And in single threading programs, your compiler or your CPU, depending, reorders your program, right, for optimization reasons, right? Let's say, for instance, you have here x equal to 1, y equal to 2, w equal to 3, and z equal to y, right? The compiler can reorder it like this, and it won't affect your program in any way, right? The compiler is smart enough to know that, oh, if I reorder this thing and make sure I just assign z earlier, right, it would not affect the outcome of this code in any way. So it reorders it, right? So, but when it comes to lock-free, reordering is very, very dicey, right? You don't always want your compiler to do unnecessary optimizations and reorder. It might break the meaning of your program. right, when it comes to lock free, because again, two threads are simultaneously accessing a data structure. So reordering in this sense can cause loss of like damage, right? I can give you an example, right? Let's say, for example, you have this thread, right? The first thread is a writer thread, right? It reads, it writes 1 to X and writes ready. Ready is a Boolean variable and assigns it to true, right? Your compiler can see that, oh, these two variables are not related in any way. I can just reorder this and maybe ready equal to 2 can come first before x equal to 1, right? It doesn't change anything in your code. And then your thread, you have another thread that is reading, right? And the thread is waiting, oh, why ready is true? I want to print X, right? If the compiler reorders this, it will read ready equal to 2 true before it sees X equal to 1. I don't know if that makes sense. So you always want to be sure that to tell your compiler, hey, reorder this, or hey, don't reorder this, right? So that's one thing with lock free that I think makes it a little bit difficult or dicey, if you would say. So you have, I think, 4 types of reordering that you can use when it comes to lock free. You have the relaxed ordering. In relax, it means, oh, you can reorder as much as you want. I don't know, optimize anyhow you want to do it. Anyhow you want to reorder the CPU or the compiler, anybody can reorder, right? And you don't really care about ordering at this point, right? And then you have the release and the acquire, right? For acquire, it means anything after, I think for the acquire and the release, both of them goes hand in hand. Acquire is mostly used to load and the release is mostly used to store, right? And for the acquire, it says don't move anything below this acquire above me. I think I would write to show an example. And then for the release, it just means everything before this release, don't move it below this release that I have here. I can give an example. Uh, um, okay, let's say you have y.load with an acquire, right? And then after it, you have this x equal to 1 here. And then maybe you have z equal to 2 here, right? And then you have, in another place, you have y.store with a release. And you have, this is another variable, a equal to 3, and you have b equal to 4 here. In this acquire, these two, they go hand in hand, right? Let's say this acquire means, okay, this x that I have here, this is a write to an x, right? I don't want this write to an x to come to this x equal to 1 to come above me. No, it shouldn't come above, right? The z equal to 2 can come below. It doesn't really matter. The acquire doesn't care. But the acquire only cares for things below it, right? Anything below it shouldn't come above me. Don't reorder it to come above this thing, this acquire here. And then for the release is the opposite. It says everything above me, right, shouldn't come below. You can move a equal to 3 above. The release does not care. But this b equal to 4 should never come below this release, this store with the release, right? And they go hand in hand in the sense that if you load something with acquire, let's say you have one thread loading with acquire, loading y with acquire, and you have another thread, this thread 2, storing something into y with a release, right? It doesn't necessarily mean that once thread 1 is loading y with acquire, it will see the write that thread 2 has done. No, it doesn't mean that immediately to see that thread, no. But it just means that anytime this thread that is loading y, let's say I loaded y to be 100, right? And here the value of y initially was 0, right? Thread 1 can load this y and still see a 0 because probably this store has not yet, thread 2 has not yet run its store at that point. But what is ensuring at this point is that anytime thread 1 sees y as 100, it means thread 2 store has happened. And it must also see B equal to 4, because remember, B must happen before this store happens. This uses a release, so it means this cannot go under here. It can't go below me. So if thread 1 sees Y as 100, which thread 2 stores it at, it means that thread 1 will always see B also as 4. It might not see A as 3 at this point, because A equal to 3 might has not happened, because loading Y, A equal to 3 happens after Y does store. So, but it doesn't really care about that. But the main thing is that any of the writes that happen before a release, right? When thread 1 sees Y's change, it will also see the writes that happen before Y was released, because it used the release acquire, right? Without these releases and all this, right? Thread 1 can see Y as 100 and still see maybe B as invalid or some other variable, maybe the past variable before it was assigned 4, right? Because we didn't put any strict ordering, and maybe the compiler has reordered B to come down here, right? So that's one thing that that's one of the ordering problems that we have. But using acquire and release, right, you can tell the compiler, oh, I want to make sure that you see this before this, but I don't care about these other ones, right? You can reorder these other ones under this release as much as you want. But you see, any write that is above this release, make sure it happens before you do this release. Right? And then for the acquire, any write that is after the acquire, make sure it happens after the acquire, not before. I don't want to see this write before I load my variable with acquire, right? So that's why I said it's just like a handshake, right? And then you have the sequential consistency. That's like one of the strictest. It means don't reorder anything. Follow what I wrote strictly. And it's one of the most expensive. That's the only thing. It's a nice, I mean, you would all like to use sequential every time. And so that we wouldn't have to think about, oh, should I use release here? Should I use acquire here? Should I use this here? We would all like to use sequential consistency every time. But the only thing is that it's expensive, right? It's one of the most expensive, because the compiler now has to follow like strict ordering. So the rule of thumb is pick the weakest ordering that keeps your code correct, right? That's just the only thing. So understanding ordering can be dicey, but once you play around with it, you get to like understand how it works. So the weakest here, I wouldn't even say it's weak. It's not weak, but the most relaxed is relaxed, because relaxed doesn't care. It just allows the CPU to do anything. And then you have the handshake, and then you have sequential consistency, which means follow all the orders. Don't reorder everything. Everything should be strict the way I kept it, right? So one thing like I was before, like, why do we even need sequential consistency? Like, it doesn't just keep the orders intact, it also does this thing called global ordering, right? I'm using this code as example. Let's say you have this atomic x, y, and a normal int r and 2 that are not atomic, right? And then this is false and this is false. And then you have 4 threads, right? The first thread is a writer thread. It's writing x equal to 2, true. And then the second thread is writing y equal to true. And then the third thread is waiting to see. Once it sees as true, it will write arrow 1 equal to y, which is 1. Sorry, which is, it depends on what arrow 1 is, but at this point, 0 or 1. And then we have this reader thread too that is doing the same thing, but it's doing the opposite with x, right? With that sequential consistency, both of them can see R1 and R2 can be 0 and 0. Let me explain. Let's say we can have the first scenario where the reader, first of all, sees x equal to true, x as true, before it sees y as true, right? So once it sees x as true, it breaks this while loop and then checks y, but y has not turned to true yet. So it still thinks that y is false. So it assigns arrow 1 to 0. Meanwhile, the reader here saw the opposite, right? It saw y as true first. before it saw X, right? And then when it saw Y as true, it now checked X. Was not true yet. So it assigned R2 as R2 to X and made R2 0. So both of them can be 0, 0. But that means our threads are seeing two different things at the same time, right? We want an ordering. We want to have, that's what makes sequential ordering interesting. We want to have global ordering. Let them see the same thing at the same time. Nobody should see, don't go and see X equal to true first before you see Y equal to true. No. If X equal to true is coming before Y equal to true, everybody should observe that specific order. If Y is coming before X, every thread should observe that specific order, right? Not one thread observing this order and another thread observing this order, and then we don't have a sync, right? They should just observe one specific order, and sequential consistency helps to ensure this, instill this kind of rules. That's what makes it interesting. But if you use relax here, these kind of things can happen, right? Where one thread saw X first before it saw Y, then another thread saw the changes to Y first before it now saw the changes to X. We don't want that kind of thing. We should agree on the order at which these things happen. Did X happen before Y, or did Y happen before X? Right? Just stick to one order. So sequential consistency helps us to have that global order, right? So the next one is compare and swap, right? When it comes to one element, let's say we have our DQ. Yeah, don't forget we are still working on the DQ. We have our DQ, and then we have the thieves and the owner. And then the thief now is stealing, and then the owner probably is done pushing tax, and all he's doing now is consume, right? And the both of them are working, coming forward, coming from the opposite end, coming together from the opposite end, and they get to the last element. Who takes that last element? How do you make sure that they are not fighting over one last element? With a mutex, it's easy, right? Because the thief will lock the data structure and then check, is this data structure empty? If it's not empty, it takes the last element and goes and release the lock. Then the owner comes and takes the lock and unlocks the data structure and check, is this data structure empty? If it's yes, it leaves and say, okay, it's empty. That means we are done here. But here, there's no lock and everybody's working at the same time, right? Everybody's working at the same time and there's one last element. How do we get to know who would take this last element without both of them taking it at the same time and thinking they both took the last element? So that's where compare and swap in atomic helps in my case, right? So compare and swap kind of helps you to know if you are the one that is going to change this particular variable, right? Because it means, hey, if this variable was 6, it means, oh, last I checked here, this variable is 6. Is it still 6? If it's still 6, that means, okay, I'm the one that gets to change it because I'm still, nobody has accessed it since. But if the variable is not 6, that means I'm not the one to change it because somebody was here before me, right? So compare and swap. Let's say the last element is 5, right? And then the thief comes and he knows that, oh, the last element is supposed to be 5, and he comes and checks, oh, the last element is 5, am I the one to change it? I have 5 here, is the last element 5? And compare and swap says, yeah, the last element is 5, you get to change it. And then it picks the last element and leaves null because nothing is there again. Then the owner comes and says, oh, I have 5, is the last element still 5? And we're like, oh, no, you came too late, the last element is not 5, somebody has taken it already. So the owner knows that, okay, I lost this race. So compare and swap kind of this helps us to know who gets the last element. I mean, but with compare and swap, there's also a risk of you having ABA, the ABA problem, right? Where but in this case, I didn't have that ABA problem, but just keep it in mind that with compare and swap, there's also a risk of you having the ABA problem, where ABA means the variable changes from A, then from B, then back to A. But the back to A is not the actual A that was there. Let's say, let me make an example. Okay, so you have the A and the B, and then back to A, right? So, and then you have 2 threads. both of them are here and they know that, and they saw A, right? You have thread 1 and thread 2, right? And they both saw A. They both saw this data structure at this level A. And then thread 1 comes and changes this to B, and then changes it back to A. But this A is not the same as this first A. But remember, thread 2 observed this as A, and it knew that the element that is in this data structure is A. So when it comes, the data structure is already here, and then it checks and say, oh, I know that the last element is A. Is this still A? And we are like, oh, yeah, it's A. But we've forgotten that this A is not the same with this A because some changes have occurred in between, changing from A to B and A. And then thread 2 changes it, right? And we can have like some issues with that. But this mostly occurs in like, I think with linking. I think mostly with if you are writing a log-free linked list. But in my case, it was a DQ, so I didn't have the ABA problem, so I was safe. So just be rest assured that if you are going to work with cars, you should put it in the back of your mind that ABA might be a problem. And there are ways to solve the ABA problem by using like versioning and the rest of that, but that's beyond this anyways. So after this, after making the QA log free, I tried to measure it and it was fantastic. And this is how far I've come. On the first part on the DFS, we had the Linux at 15 seconds and we had the Windows at a minute and 5 seconds. Then after we introduced the simple traditional thread pool, we had the Linux at 10 seconds and then we had the Windows at 7 seconds. And then when we did the stealing, when we tried to make other threads steal from other threads, we had the Linux at 8 seconds and then the Windows regressed to 12 seconds. And now with log free, when we remove the log contention in the stealing part, right, we had the Linux now at 2 seconds, 2.8 seconds, and then we had the Windows at 5 seconds, right? So, I mean, I think I tried to stop here because I don't think I could go any further. But this does not mean that log free is always the answer to things, right? As you can see, at some point I felt that work stealing would actually even be better than the traditional thread pool, but unfortunately it wasn't, right? So I think one thing you have to put in mind is benchmarking every time, benchmarking at every change you make, just to be sure that, okay, I'm actually making substantial progress. I'm not just complicating things for myself and I'm not making any progress with the speed, right? So I think that's it. For any more, I think to understand more about log-free and all of the CPU caches and how they work and the memory ordering specifically, I would suggest you watch. I think there's a talk that Scott Meyers, I don't know if I'm pronouncing his name right, he had on CPU caches and why you care. I think he went in depth on the CPU, how it works, how the memory ordering works, and all the cache lining validation and all of that. And then we also have like Helpstotter's talk on log-free programming. I think these are old talks, right? But they will help give you like an in-depth before you now come to the most recent CPU talks on log free. Yeah. So I think there was also a talk I was watching this week by the guys from Jane Street. But that one was Rust specific, but it works with C++ too. I mean Rust and C++ are it works with C++ too. Even this there's this book by Marabos, Rust Atomics. I think for me, the Rust book explained memory ordering more than all other C++ talks I read, in my opinion. The Rust explained the memory ordering better than the rest of them, but I would say a great place to start would be this first talk. It will give you a little bit of in-depth of how like the CPU caches work and then the memory issues, and it will give you like an introductory to log free and even trading too. Yeah. And then you can probably explore this other one. Maybe I will drop the link in the chat or something. And I think that's it. If you have any question, you can ask. For the code, I have it on my GitHub, and then to see any of I made it easy to see any of the changes. If you want to go back to the time of the DFS, when it was just DFS, every change is a commit, right? Every commit is a change. You can see the thread pool changes, how the repository was when it was just the traditional thread pool. And then when I went to work stealing, each change is an actual commit. So you can just go back to one commit and then see what the changes were like. Can just go back one commit. Yeah. So I think that's it. If you have any question, just let me know. And I will try my best to answer them. Okay, so any questions? Okay, if there's no question, I give the mic back to Mr. Benson, the moderator.
Hi Jennifer. I I I think I really have you considered I don't know, I tried solving issues relating to this kind of problems, but have you considered using atomics? Are you considering trying to see how atomics can help you? I don't really know how it's going to help you, but I'd really be happy if you can let us know if
Okay. Oh,
atomic.
okay. I think you're mistaken. When I say lock free, that's atomics. So the whole lock free shenanigan is just atomics.
But you see, um, I don't know how to to explain what I'm trying to ask. So you were not using like the OS atomic functions, but you were using like you're trying to do log contexts yourself, right? By creating your own DQs and stuff.
Yes, but the DQs use atomics. Like, like
How
if you have
they
if
atomic functions?
yes, okay, let me
Okay.
explain. Let me use a simple vector to explain. If you're writing your own vector class, let's assume you're writing your own vector class, right? You need indexes to keep track of the back, right? Let's say you can use let's say you use an I to keep track of the back. So when you push back to the vector, you increment I, right? And then when you pop from the vector, you decrement I, right? That would be how your vector would work. So that I, it would be atomic. It would be std atomic int I when it comes to log free. That I is what would be atomic because the I is what we are using. The I is what we use to know that somebody has incremented. If you want to check the size, right? The size just returns what is I. Is I 0, 2, 1? That would be what size of your vector is. So that variable I is what would be atomic. So that's what basically makes the data structure atomic because every thread is fighting for I. If I want to add something to the variable, to the vector, right, I would want to increment I to show everybody that, hey, I have added something to this vector. So I plus plus. If I'm taking something from the vector, I would want to decrement I. So I want to do I minus minus. So every thread is fighting for that specific I. So it's the I itself that would be atomic.
Hmm.
That is what basically makes the data structure lock free. The fact that the indexes that you use to get access to the data structure is atomic. That's what makes the data structure atomic itself. Not like there's a specific uh, magical thing there.
Oh, no, okay. I think maybe I missed it in your talk because I Maybe I lost track of.
Oh, okay. So lock free, when
Yeah.
I say lock free, basically just means I'm using atomic. I'm using atomic store, I'm using load. But then
Okay.
when you're using those stores and load, you also want to tell, do we want to, what memory order do you want to use this store with? Is it a memory order relaxed or sequential consistency, or is it a memory order release? Exactly. So you
Okay.
have to specify what memory order you would be using.
Okay. I thought you were doing the fights like manually
No.
tracking. Ah,
No, not at all, not at all. The only time I was doing the fight manually was when it was not lock free, like when you had like the normal stealing with the lock contention. That was easier because you would just say, just pick up, right? Just check, and then have access, take access to the mutex, right? So
okay. All right. All right. All right. Yes.
sorry,
That.
sorry. I'm seeing some questions here. Lack of causes race condition. No, not sure. Race condition is different. Race condition cannot happen. I mean, race condition can actually happen in log free. But when people talk about race conditions, it's just basically most in mutexes, right? When two threads are trying to make changes to a specific data structure at the same time. So you kind of use mutexes to stop it. But yes, race conditions can happen in lock free, but sequential consistency, lack of it does not cause race condition. What it causes is lack of ordering, right? Like I said, I can have x equal to 1, y equal to 2, right? But thread A can see y equal to 2 before x equal to 1. And thread B is seeing x equal to 1 before y equal to 2. They are not seeing the same thing at the way it's supposed to. Like if I write a program and I write x equal to 1 and y equal to 2, and if Mr. Benson comes and reads my program, he's seeing that x equal to 1 comes y because before y equal to 2. Everybody agrees with that. But the CPU can change things. So with sequential consistency, you are saying don't change this thing. So it will not cause a race condition, but it will cause kind of like an inconsistency in your code, in which maybe some things are delayed or some people are not seeing the same thing at the same time. Because in as much as like something like the CAS, right, compare and exchange, it was one issue I was having that I was questioning when I was writing one of the codes, because I couldn't see the need for the sequential consistency because we had CAS there, and CAS was making sure that the winner will make changes to the elements. So why do you still need sequential consistency? But the thing is that doing that CAS is expensive, right? Because you chose lock free because you want to help performance, you want to improve the performance, right? So you want to make the tiniest changes. Like I said, sequential consistency is expensive. It's more expensive than something like relax or something like acquire and release, right? So and you chose to use lock free because you're looking for something fast. So why now mess up the algorithms that will in the lock free and make it slower, right? So something like CAS is expensive, right? So even if you know that okay, this CAS is going to fail, even if it tries it to fail, it's not like CAS will prevent. CAS is expensive, so you want to always prevent not going into that CAS mode. So you can use these ordering rules to like I don't know how if I'm explaining it right, but I think I wrote a blog on it and you can check out that blog. I think I tried to explain as much as possible anyways. But no, sequential consistency is not what causes race conditions basically. It's not what causes race conditions. What causes race conditions is just the two threads trying to access things at the same time. Just But sequential consistency, no. You just make sure that both of them are seeing the same thing. No, we are not seeing different things at different timelines. They are observing the elements at the same way. If we are agreeing that it's x before y, we agree that it's x before y. If it's y before x, all the threads will see it as y before x, right? So yeah,
All right, thank you for the response. But then I just want to add something.
yeah,
Okay, maybe at the end of this meetup, you can drop some of your resources. We have a dedicated repository where you can push some of your resources on the slides so that others
oh,
can have
okay,
access to it. So basically, that's it. Well done once again. You really did a great job. We are looking
okay,
forward to
okay.
having you. We are looking forward to
Okay.
having you some other.
Okay,
Yeah.
sure. I mean, I'm trying to have a, I don't know if that's, I mean, that's future tense anyways. I'm trying to add like the scanner to be able to find duplicate files. So doing something like hashing and parallel hashing. So maybe if I figure that out, I can talk about it on. If I don't figure it out, fine.
All right. I don't know. Is the project still live? Are you still working
Yeah,
on it?
yeah.
Maybe.
Um, I mean, for the part of this part, I'm done with it. Like I said, I'm done with it, and you can check it out. Every commit is a specific level. If you want to go back to when it was just the traditional thread pools, you can go back. You can see the commit there and go back to it. If you want to go back to when it was just DFS, you can go back. If you want to go back to when it was the work stealing, you can see every commit is a change. So the project is just is there. It's on my
All
GitHub,
right.
I think.
All right. I'd love to look at it. It's all right. Thank you very much.
All right, thank you. If you have any questions, you can drop it on the chat anytime. I can answer. I'll try my best to answer.
Sure, definitely.
So
Okay.
there was a
All
video I
right. I'm
watched.
greeting. I'm greeting
Sorry.
my Jean. I'm greeting Jean, my boss. So I'm seeing his comments. So I'm greeting.
Okay. Okay. Jean-Philippe, how are you?
Okay. I think thanks for the opportunity to have this talk.
I'm
Yeah.
doing great. I have some off top of you
Sorry,
did
I
a great
cannot hear
job.
you. Your voice is cracking.
I only have this get on. Yeah, a nice talk.
I can't hear you, Jean. I don't know if I'm just the one.
No, it's also breaking up for me.
But anyways, thanks for having me talk about this. And like I said, if you have any questions, you can always drop it anytime. I would make sure to yeah answer as much as I can. But yeah, going log free is uh, to be honest, I don't think anybody can know it all. So just watch lots of talk and read lots of things. So
There's actually
yeah,
a
my boss
talk.
was a C plus plus person first. I didn't know, but her this thing, her blog on the Rust Atomics really was, I think for me, was better than any other C plus plus stuff out there. For me, basically, it helped me understand better than any other C plus plus resources I could find out. So
Yeah. So there's something that I watched. I think about 2 weeks
okay,
or
I
so.
think that's it for me. I'm handing over to Mr. Benson now. So
Okay. Just check. Can you hear me?
Yep,
Yes, I
we can
can hear
hear
you.
Oh, okay. Fine. So I was thinking about you see the structure of your talk was about steps that you've taken. There's a talk I watched from CppCon, I think last year. It's a talk, I'll post it somewhere in the chat when I get a hold of it. But it was about threads versus coroutines. And one of the core things that the highlight of the talk was that threads are operating system constructs, but coroutines now give us, the developer, a chance to kind of like have full and total control. So there are ways to make it a
okay, I
bit more
think I have.
efficient.
Let me get the link to the.
So my point was, have you thought of exploring this as a next step, like with coroutines?
Okay, sorry. Where did you said I could drop a link where in which is it in this
No,
project
I
in
said
this project room or
you could do it
did
in the
you really
general
put
chat
it
or even in the meeting room chat, whichever.
or in the CPP general? Which one?
CPP general, I think, would be better. So I've posted a link to the video I was talking about. So the question was, have you looked into using coroutines I mean, especially now that you're really deep into managing, I mean, you really understand all of the sequencing issues with threads. Coroutines is like it's in the same ballpark, just that many people don't quite haven't quite ventured that direction. So just asking whether it's something you have thought of or explored.
Hello, Jennifer, can you hear
No,
us?
I can't hear. I can't hear you. Okay, I can hear you. I can hear you, but I didn't hear any other thing before that.
Okay. Oh, Mr. Matthew was asking about coroutines. Have you explored using coroutines in your project? And he posted a
Yes, I
link
have.
about current threads and coroutines.
Yes, I have, which is why I am planning to do, because like I said, the goal of the project was to use C++ 26 features, and coroutines was like on my to do. Coroutines and modules were the first thing, but apparently using coroutines would damage more than. But yeah, that's why I'm trying to do this. I'm trying to do the parallel hashing. Yeah, with the parallel hashing, I'll be using coroutines, so hopefully I get to explore it. That's why I want to do the hashing. So it's kind of going to be like another feature in the project where when you give, like, it's a CLI tool where you give it a root directory, right? When you give the root directory and then it scans, you can also check the root directory for duplicate files, right? Duplicate files. So in that sense, I need to be able to hash and know that two files are actually the same, right? So I hopefully I would use coroutines in that sense. But in this directory scanning, it was just straightforward. There was no need for me to use coroutines.
All right, good.
Okay, I'm curious how Atomics works properly with the coroutines.
I think I've used them as well, but I'm curious about your insight on how it would work with coroutines, how different it would be or
Okay,
something.
maybe if I'm able to hack it, if that is a huge if, oh, it's a huge if. If I will let you know if I'm able to do it. But I've started, so let's see how that goes.
Okay, thank you.
All right, I think I'll just give kind of like shout out to those who have not spoken. Nakuru,
Okay, so I was
Michael.
asking where should I drop, on what channel should I drop the resources and the link?
Sorry. I'm sorry, Jennifer. You keep talking over Mr. Matthew.
Oh,
What's happening?
okay.
You can't.
I can't hear Mr. Matthew. He's on
What?
here. I'm seeing error on his own this thing. I'm seeing error 2012. So I can't even hear him.
It's probably a local Discord issue.
Yeah.
But
Usually.
Matthew, do you hear Jennifer?
Yes, I can hear her fine. But most likely, you see, there was a point, the connection, I wasn't getting her screen at some point earlier.
But I can hear every other person.
So I reset everything. So maybe the
Okay.
connection has not reset.
Okay. So how we do it? Because Mr. Matthew is the moderator. Uh, or let me assist, or let me
Okay, yeah.
here.
He's trying to. I think he's shouting out to Nakura and Michael. So you guys are uh, new to the community. So would you want to introduce yourselves or talk about yourselves?
Hi everyone.
Hello.
Okay. So my name is
Oh, okay.
Matthew
Sorry, I
Whitney.
think I muted Nakul earlier.
No, I can hear him.
Okay, but can you hear me now? Over.
Yeah, I can hear you.
Yeah,
Yes,
I
yes,
can
I
hear
can.
you.
Yeah. So my name is Matthew Whitney. I'm a Nigerian-based software engineer, stroke computer scientist, and most of the things I do is just web development, mobile app development, and C++ programming and stuff. I'm happy to be among to like keep an important talk about that training.
Okay, thank you. Thanks for the introduction, Akuru.
Thank you.
I've
You're
been
most welcome.
Okay.
And please, I want to ask a general question. Who has worked on networking like code, like C++ networking code before?
I think I've only
What level? What level of the networking stack?
Like doing a DMA from your network card. Let's say if it pushes the packet byte into memory, and then you're supposed to allocate it for them to process the network packets to the in the kernel, the to whatever application that you are, and maybe you are receiving your data on to like at the hardware software layer.
Okay, so that's very low. That's like sockets or even below sockets.
So okay, I haven't done that. Just
Well, anyone can answer.
Yeah, I think you see C++ is generally just low.
Oh, I haven't too. I haven't done any of that before.
Yeah, so I was saying, Emmanuel, you can hear me, right?
Yeah, I can hear you. I'm just,
Okay, so I was just saying that generally, you see, C++ just gives you access to whatever operating system you're on. So you see, that's what I mean. We don't necessarily have like a specific actually it depends on which system basically you're talking about. So I think I've only played around with like sockets, which is more like a C like thing, but that's just just for learning. But I've not really done anything practical with it, because I mean it now ties into what Uzo was talking about with the web, the web frameworks, which kind of like do all that stuff for you. So I think I don't know if that would kind of like satisfy what you're asking.
yeah. I would also want to add that if you look at Boost Azure, Boost Beast, even if you don't use the libraries, their internals or zero MQ, they have as Mr. Matthew said, because some of these things are very OS specific and they're exposed through the OS libraries, system libraries. Some of these libraries help to aggregate them and provide a common API for you to work with. So that you don't have to be very to write on cross-platform code. So Boost Azure, they handle a lot of the manual packets and sockets manipulation on all the popular OSs, right? I think ZeroMQ also does that, but ZeroMQ goes further and exposes it in a form of API, in a form of sockets API. Everything is like a socket API. So then for Boost Azure has different models for different kinds of both of them generally have both of them. So you can look at those two, the implementation for it. And I think HFTs they have the for DMA there's some libraries that they publish. If I find out, I'll probably drop some links that you can use to actually manipulate from the raw OS libraries. There's also directly using EPOL, KQ, and IOU rather than using the standard rather than using the normal sockets. So those are the various approaches that you can use to really, really, really optimize your networking if that's your focus.
okay. So when you find you said you'll be looking
I'll
out.
do things, yeah.
Yeah. So when you find them, I just wanted to ask about it and see if anyone. It's something I'm just interested in doing. So I just wanted to see if anyone had any experience or.
Okay. Yeah, so I want to mention that since we have a guest speaker around, so Jennifer, we normally after all our
talks, we have like an optional community style conversation where everybody can just pitch things or
Okay.
yeah. So you could stay as a community member.
Okay, sure.
Yeah, and but then we can. But I think if anyone has any more questions concerning our talk, we can ask them now, and if not, we continue with the community style conversation. Okay, so since there are no more questions, uh, now back to the community style conversation. Do does anyone have any talk, especially you, Nakuru and Michael? Do you have any ideas for any talk that or any talk or topic that you want to present on? It could be on your former work or excerpts from your workplace or from personal projects, and or it could even be back to basics style talks like iterators, coroutines. You could talk about coroutines like Jennifer is mentioning. So yeah. Does anyone have? You can add them so that we can plan further and also schedule a date for this.
So I think we can kind of like formally close this month's session. For those who can hear me, I want to say thank you very much for taking the time. Thank you for being with us. Thank you for, just being part of the community and helping us to gain the confidence to share. I'm very grateful to Jennifer. I don't think she can hear me, but I just wanted to say thank you for those who have come, who can hear me. Then I guess I'll hand it over to Uzo to kind of like close us off. Then we can, anything else will continue in the chat, just, in case anything comes up at a later time.
Okay, thank you, Mr. Matthew. All right, so there's nothing else from my end. We would gather all the resources that Jennifer mentioned, and we would see if we can post them on the chat as well. Then yeah, please feel free to continue any conversation we had here on the in general channel, especially this networking. I would also see if I can drop those things here. Thank you all for joining. I hope you have a beautiful weekend. Bye everyone.
Okay, thank you. Bye.
Thanks.
Bye.